Hey everyone, Sarah here from DBT Labs. I'm excited to explore our next topic today in our Fusion Fundamentals series. Last time we talked about SQL comprehension and how with the DBT Fusion engine, DBT now goes beyond simply reading your SQL to actually understanding it. Today, we're going to go a little deeper to take a look at how the Fusion compiler helps make that possible. So let's start by talking about how DBT Core works today. With DBT Core, there is something called compile. You might have used the DBT compile command before, right? And historically, this meant let's take this SQL code and this Jinja and render it into a full executable SQL statement that I can then send to my database. And this enabled a huge step forward with regards to best practices, but ultimately, this is really just string templating. And that is different from Fusion, where after Fusion renders the code, there's a compile layer that produces a logical plan for every query and then runs static analysis on that plan before execution. So let's break that down. What is a logical plan? You can think of a logical plan as a fully typed, validated blueprint for your query. It shows you which tables are scanned, which filters apply, what each expression returns, and how column types flow and change. If you've ever run an explain query in your warehouse, you've actually already seen a logical plan. The difference here is that Fusion builds one before sending it to the warehouse, ensuring that it'll run when it gets there. And what's happening here under the hood is that we have a compiler binding metadata like function signatures and schema types to the parsed syntax tree to create a resolved syntax tree. And this is what gives the resulting logical plan full data type awareness. Once Fusion has built this logical plan, it can start asking deeper questions through static analysis. At this stage, the compiler is validating the query against the state of your warehouse, checking that the columns and tables it's referencing actually exist and that the plan is semantically consistent end to end. For example, if you call date add with arguments in the wrong order, a parser might see valid syntax here, but the compiler reasons about the semantics, meaning that it knows that the second argument must be an integer, not a timestamp. And this error is caught before you ever hit the warehouse. So producing and statically analyzing logical plans provides a simple but very powerful promise. If your project compiles cleanly in development, it will also run without compilation errors when deployed. You can trust that the SQL itself is structurally and semantically valid for your warehouse. And this reliability is built right into the compiler, which means faster and cheaper feedback for you. So hopefully this gave you a better sense of how SQL comprehension actually works and just how much the compiler is doing behind the scenes. If you want to try it firsthand, go install Fusion and take it for a test drive. Until next time.